So enthalpy, again, enthalpy was something we covered first semester. That was delta H, talking about the heat of any sort of process. Remember, a negative value was exothermic, a positive value was endothermic. Typically, an exothermic thing we'd label as spontaneous. Because if a process has enough energy to do what it needs to do, and it gives off energy, that lends itself to being something that is spontaneous. What we have to go over today is that the idea of spontaneity, that a process will occur without extra help needed, goes beyond enthalpy. And entropy is one of the steps, and then in the reading guide, you're going to be introduced to Gibbs free energy, which is the ultimate determination of whether or not a process is going to happen on its own or not. And that idea of spontaneity is the main topic within thermodynamics, I would say. And within that Gibbs free energy, both enthalpy from last semester and entropy today are in that. So entropy, kind of unusual. It's the measure of disorder of something. I don't think this next slide you actually have to write down. Just kind of going over the history of it. This was figured out by someone named Boltzmann. And that capital W, so this equation on the second bullet point, you do not need to know. However you read your book, it will refer to Boltzmann, and that W refers to microstates. Microstates might be easier to think of as ways that you can arrange this. For example, we have a seating chart right now. We could change that and rearrange that. We could change it and rearrange it again and again and again and again. When we have 22 students in this room, there is a lot of different ways that we could arrange you. If we only had 2 students in this room, there's only so many ways that we could arrange you. Now, that arrangement goes into more than just the number of particles. It goes into states of matter as well, and even some compounds have more disorder than other compounds do. So this idea of disorder and arrangements is what entropy is based upon. Okay, so first law of thermodynamics we covered last semester. Energy can't be created or destroyed, just transferred. So that was used with enthalpy. Entropy covers the second and the third laws of thermodynamics. So first off, my bullet point here, absolute zero is a temperature that we should hopefully be familiar with. That's 0 Kelvin. At 0 Kelvin, particles would cease to move. And if there is no movement, there is no disorder. They are in a fixed position. Even you guys right now have some movement occurring. Again, we're breathing, we're writing, we're moving around a little bit in our chair. Also notice with this bullet point, a perfect crystal. So there has to be structure to it. Once all of a sudden we have desks moving all around the place, we are not as orderly as we are right now in nice even rows. But if the desks were just scattered all about, I would not call that pure order. There's a little disorder to that still. So this idea of entropy is based upon the fact that at absolute zero, if you have no impurities, so you're the same thing throughout, because when I say perfect crystal, yes, I'm referring to the structure, but even what if instead of Kate Beckman, we substituted in a 42-year-old man? There's disorder now in this room. Or a 3-year-old child. There is now a little bit more disorder. It's not the same throughout. Now, we can look at the phase notation of a particle and identify how much order is within it. By the way, after the AP exam, again, we do some fun stuff here and there with labs. Again, we do the scuba. There's actually a video I'm going to show you. So we're going to do a video day, or half a day at least, in AP Chem, where when I was writing the new AP curriculum a few years ago in my house, the TV was on, and all of a sudden, someone mentions the second and third laws of thermodynamics, and they talk about entropy. I'm like, man, what are they talking about? They're talking about how the universe is going to end millions of years from now. and it's all based upon entropy. So we're going to watch that video afterwards. We can't do it yet because we have to actually learn right now, but after the AP exam, we can have fun. Think about it. Gases are bouncing around. There is no specific way that they bounce around that we can predict. They have a lot of disorder. Liquids have a flow about them. So liquids have, they're still kind of stuck together, but they're not all flying out in all directions. Solids are in a structure that are just vibrating, kind of like how you're sitting right now. So solids have the least disorder of the three primary states of matter. Which brings me to my question then of where do you think solutions fit in from solid to liquid to gas to amount of disorder? Yeah, between gases and liquids is where a solution would fit in. Because a solution like a liquid has a flow about it, but there's more than one thing. It's a mixture. So sometimes I even have students write down, kind of a hierarchy. You have gas, you have solution, you have a liquid, you have a solid. And this is increasing in entropy. We could even predict if it wasn't just based upon state of matter, but it was also based upon number of particles. For example, if you had a decomposition reaction, recall decomposition reaction starts with one reactant, it breaks down into, let's say, two products. Let's say that it was the exact same state of matter, a gas to start with and two gases to end with. Well, if it's one gas on the reactant side and two gases on the product side, the product should have more disorder than the reactants. Because if you have more particles, there's more arrangements. Again, more students in here, more ways that we can arrange it. Here's my very last point, and then we are done with notes. Again, this was just meant to be a quick introduction before we get into the reading guide. If a process has more disorder, more entropy than it started with, it is a spontaneous process. Spontaneity, whether or not something will occur kind of on its own, is a big topic. Enthalpy covered it first semester. Entropy covers it now. Gibbs free energy is going to cover it as well. Now, if you want to think numerically, enthalpy, remember delta H, a negative value was exothermic, meaning that it was spontaneous. Unfortunately for you, entropy is the exact opposite. A positive entropy value means spontaneous because there is more disorder at the end. Again, up on the whiteboard, one of the equations that you're going to be working with when you do some practice problems is the entropy of all the products minus the entropy of the reactants. Products minus reactants we might be familiar with because we did that with delta H as well. But you're going to be introduced to a couple other equations today with the reading guide. And then next class, I'm going to kind of give you, again, very brief notes on all of the different equations dealing with Gibbs free energy. Because we can actually relate Gibbs free energy to electrochemistry. We can relate it to equilibrium. And then also enthalpy and entropy, things like that. Which is kind of what our lab next week, Monday, is going to be, is we're going to do calorimetry. So we're going to figure out some enthalpy. We are going to do some electrochemistry to figure out our delta G. From there, we can calculate our delta S. So we're going to have a pretty good review of some of the stuff that we've done before, because it all ties in together nicely when we come to this final topic of thermodynamics.